The reference codes all apply. Section 430.6b requires that the motor branch circuit conductors be sized to carry the motor's full load current. Section 430.22c requires that the motor branch circuit protective device be sized to carry the motor nameplate current plus any additional inrush current. And Section 430.22e requires that the motor branch circuit conductors be sized to carry the maximum inrush current of the motor. In the described scenario, the motor nameplate current is 36 amps for the 4-pole configuration or 56 amps for the 2-pole configuration. The maximum inrush current is 164 amps for the 4-pole configuration or 256 amps for the 2-pole configuration. Therefore, the motor branch circuit conductors must be sized to carry 256 amps. The next question is whether to use 1 American wire gauge or 4 American wire gauge conductors. According to Table 310.16 in the National Electrical Code, 1 American wire gauge conductors are rated for 230 amps, and 4 American wire gauge conductors are rated for 100 amps, assuming that the conductors are rated at 75 degrees Celsius. Therefore, 1 American wire gauge conductors must be used for the motor branch circuit conductors. It is recommended to also use 1 American wire gauge conductors for the high-speed windings and 4 American wire gauge conductors for the low-speed windings. This is because the high-speed windings are rated for 36 amps, and the low-speed windings are rated for 56 amps. Finally, apply all of the rules in 430.6, 430.22c, and 430.22e to the installation. This will ensure that the motor is properly protected and that the installation is safe. When selecting conductors, it is important to consider the ampacity of the conductors, the ambient temperature, and the type of insulation. The ampacity of a conductor is the amount of current that the conductor can carry without overheating. The ambient temperature is the temperature of the air surrounding the conductor. The type of insulation is the material that is used to insulate the conductor. When selecting conductors for a motor circuit, it is important to select conductors that are large enough to carry the motor's full load current and inrush current. It is also important to select conductors that are rated for the ambient temperature and the type of insulation that is used. In addition to the above, it is also important to consider the voltage drop in the conductors. Voltage drop is the decrease in voltage that occurs as current flows through a conductor. Voltage drop can cause problems with motor operation such as reduced torque and speed. To minimize voltage drop, it is important to select conductors that are large enough to carry the motor's full load current and inrush current. It is also important to keep the length of the conductors as short as possible. Motor branch circuit protection is required to protect the motor control apparatus, and the conductors against overcurrent due to short circuits or grounds. The motor branch circuit protection devices are sized based on the motor's full load current. The overcurrent protection device protects the circuit from excessive current which could cause overheating or damage. There are several types of overcurrent protection devices, including fuses, circuit breakers, and motor overload relays. Fuses are one-time devices that melt when the current exceeds the fuse's rating. Circuit breakers are resettable devices that trip when the current exceeds the circuit breaker's rating. Motor overload relays are designed to protect motors from overheating due to overload conditions. Motor overload relays trip when the motor current exceeds the motor's full load current for a specified period of time. When selecting motor branch circuit protection devices, it is important to select devices that are properly sized for the motor's full load current and inrush current. It is also important to select devices that are rated for the voltage and current of the circuit. To determine the minimum conductor size for the described torque motor, several factors need to be considered, primarily based on the National Electrical Code, specifically Article 430, which covers motors, motor circuits, and controllers. First, identify the full load ampacity, or flaw, for both operating speeds, which are 36 amps for the 4-pole configuration and 56 amps for the 2-pole configuration. Also, identify the locked rotor amps, or LRA, for both speeds, which are 164 amps and 256 amps respectively. Now determine the appropriate conductor ampacity. For NEC 430.22, the branch circuit conductors supplying a single motor shall have an ampacity not less than 125% of the motor's full load current. The higher of the two FLA values must be used because the motor can operate at either speed. Therefore, the calculation is 56 amps multiplied by 1.25, which equals 70 amps. This means the conductors must be rated for at least 70 amps. Then, verify the conductors can handle the inrush current. While 430.22e is mentioned, it's essential to understand its specific application. For motors with marked locked rotor current, the conductors must be capable of carrying this current. However, the overcurrent protection device is what primarily handles and clears fault currents related to the locked rotor condition. The conductors should be sized to withstand the thermal and mechanical stresses during such events for the duration it takes the overcurrent device to operate. Next, select the conductor size based on the ampacity calculations. Consult NEC Table 310.16. This table provides ampacities for various conductor sizes based on insulation type and temperature rating. Assuming the use of conductors with a 75 degrees Celsius insulation rating, which is a common standard, 4 American wire gauge copper conductors have an ampacity of 85 amps, which exceeds the calculated minimum of 70 amps. Therefore, 4 American wire gauge would be the minimum size based on ampacity. However, the high inrush current needs to be taken into consideration. Now address the voltage drop. Although not explicitly mentioned in the provided information, voltage drop is a critical factor in motor circuits. Excessive voltage drop can lead to reduced motor performance, overheating, and premature failure. A common recommendation is to limit voltage drop to no more than 5% from the source to the motor. Use voltage drop calculators or consult NEC Chapter 9 Informative Annex D for guidance on calculating voltage drop based on conductor size, length, and current. If the initial conductor size results in excessive voltage drop, a larger conductor size may be necessary. Then consider the motor starter and controller wiring. The wiring between the motor starter or controller and the motor itself must also comply with NEC regulations. These conductors are typically sized based on the motor's full load current and the requirements of the motor starter or controller. Ensure that the conductors within the controller are appropriately sized and rated for the application, and verify compliance with other NEC articles. In addition to Article 430, other NEC articles may apply to the motor circuit installation, such as Article 250 for grounding and bonding, Article 300 for wiring methods, and Article 310 for conductors in general. Make sure to comply with all applicable requirements. Finally, document all calculations and conductor selections for future reference and inspection purposes. Proper documentation can help ensure the safety and reliability of the motor circuit installation. In summary, based on the provided motor nameplate data and the applicable NEC requirements, the minimum conductor size for the torque motor branch circuit would likely be 4 American wire gauge copper conductors, assuming a 75 degrees Celsius insulation rating after considering the motor's full load current and inrush current. However, a thorough voltage drop calculation and consideration of other NEC requirements are essential to ensure the final conductor selection is appropriate for the specific installation. Always consult with a qualified electrical engineer or licensed electrician to ensure compliance with all applicable codes and standards. To further elaborate, consider the practical application of these calculations and code references. Let's consider the specific scenario of the dual-winding torque motor. The fact that it can operate in both delta and Y configurations and at two different speeds, which are 2-pole and 4-pole, adds complexity to the conductor sizing process. The NEC provides guidelines, but the engineer or electrician must apply these guidelines thoughtfully, considering all operating conditions. The reference to section 430.6b highlights the importance of using the motor's nameplate current to determine the conductor size. The nameplate provides the FLA for both the 4-pole and 2-pole configurations. As noted, the higher of the two values must be used because the motor could operate at either speed. The reference to section 430.22c addresses the sizing of the motor branch circuit protective device. This device, which is typically a circuit breaker or fuses, must be sized to protect the motor and conductors from overcurrents. The protective device must be capable of carrying the motor's starting current, which can be several times the FLA. The reference to section 430.22e further emphasizes the importance of considering the motor's inrush current, also known as the locked rotor current, when sizing the conductors. Although the conductors are sized for 125% of the full load amps, it's important to check that the conductors will be able to withstand a locked rotor event from a thermal perspective. The mention of table 310.16 is crucial. This table provides the ampacities of various conductor sizes, based on their insulation type and temperature rating. The table is essential for selecting conductors that are capable of carrying the required current without overheating. The example of 1 American wire gauge conductors being rated for 230 amps and 4 American wire gauge conductors being rated for 100 amps illustrates how table 310.16 is used to determine the appropriate conductor size. It is important to note that the ampacities in table 310.16 are based on specific conditions, such as the ambient temperature and the number of conductors in a raceway. If the actual conditions differ from the table's assumptions, correction factors must be applied. The recommendation to use 1 American wire gauge conductors for the high-speed windings and 4 American wire gauge conductors for the low-speed windings reflects a practical approach to conductor sizing. Since the high-speed windings are rated for a lower current, which is 36 amps, than the low-speed windings, which are 56 amps, smaller conductors can be used for the high-speed windings, which reduces the cost and complexity of the installation. However, it is important to ensure that the conductors are still capable of carrying the motor's inrush current. Finally, the advice to apply all of the rules in 430.6, 430.22c, and 430.22e highlights the importance of following all applicable codes and standards. This will ensure that the motor is properly protected and that the installation is safe. To expand further on the practical application of these NEC sections, let's delve deeper into how they intertwine in a real-world scenario with the dual-winding torque motor. Imagine a motor is installed in a manufacturing plant powering a critical piece of machinery. Downtime due to electrical issues can be very costly, so proper conductor sizing and protection are paramount. Section 430.6b acts as the foundation. The nameplate provides the FLA for both the 4-pole and 2-pole configurations. However, what if the motor frequently switches between these speeds? In this case, the highest FLA, which is 56 amps for the 2-pole configuration, dictates the minimum conductor ampacity. Now 430.22c steps in to address the overcurrent protection. The circuit breaker or fuses need to handle not just the FLA, but also the potentially high inrush current during motor startup. Torque motors, especially under load, might exhibit significant inrush. The engineer needs to consult motor performance curves or conduct measurements to determine the actual inrush current. If the inrush is substantial, a time delay fuse or inverse time circuit breaker might be necessary to prevent nuisance tripping. Next, 430.22e adds another layer of complexity. It mandates conductors capable of withstanding the locked rotor current, which is 256 amps. This isn't just about ampacity, it's about the conductor's ability to withstand the mechanical and thermal stresses during a locked rotor event, even for a short duration. This is where conductor material and insulation become critical. Copper conductors are generally preferred for their higher conductivity and ability to withstand heat. Insulation types like THHN or XHHW are common choices, but the specific rating needs to be carefully selected based on the ambient temperature and the installation environment. Now consider the recommendation of using different conductor sizes for the high-speed and low-speed windings. While seemingly practical, this approach requires careful engineering and clear labeling. If the motor control system allows for independent energizing of these windings, then separate conductor runs are feasible. However, If both windings can be energized simultaneously, the conductors need to be sized for the combined current, and voltage drop, often overlooked, can be a major issue. Long conductor runs, especially in industrial settings, can lead to significant voltage drop, reducing motor torque and efficiency. The engineer needs to calculate voltage drop under both full load and starting conditions to ensure it remains within acceptable limits. This might necessitate upsizing the conductors beyond the minimum capacity requirements. Also, the installation environment plays a critical role. Is the motor located in a hot, dusty environment? Are the conductors run through conduits or open trays? These factors affect the conductor's heat dissipation capabilities, and directing factors need to be applied according to NEC tables. For example, if multiple current-carrying conductors are bundled together in a conduit, their capacity needs to be directed to prevent overheating. Finally, documentation is key. The engineer needs to create detailed drawings and calculations outlining the conductor sizes, overcurrent protection, and voltage drop analysis. This not only ensures compliance with codes but also facilitates future maintenance and troubleshooting. Without proper documentation, identifying the correct conductor sizes and protection settings can be a difficult task. In conclusion, sizing conductors for a dual-winding torque motor isn't a simple cookbook exercise. It requires a thorough understanding of motor characteristics, NEC regulations, and the specific application and environment. Engineers and electricians need to carefully consider all factors to ensure a safe, reliable, and efficient installation.